choose like the wrong term on the right-hand side, basically. Listen, I will send you guys. See, you can see up at the top. This is on my website, so you can look at this page. It's page 9 in these notes. Most of the other examples are probably irrelevant to you, so you don't. I'm not saying you gotta study this PDF or anything like that. I'm just saying this particular example is the one we went over today because it's relevant. Yeah. Yep.
So at the start, you made a v equals y to 1 minus n. How did you determine to do this?
Oh yes. So as I was saying, remark 5.6 on page 14. It says that whenever you have something like this, dy dx plus p of x times y equals to q of x times y to the power n, that suggests making a z equal to y to the minus n plus 1 substitution. Now, I had v equals to z in the thing we're looking at the moment here. All right. So sometimes people use a v for the substituted variable. Sometimes people use a z. You could put a Pac-Man there if you wanted. Pac-Man's not a very efficient symbol to do calculations in, though. I don't recommend it. So this is remark 5.6 in the notes. It's basically just that. So to answer your question, Taylor, more specifically, in this problem, y is equal to the original problem that I've scrolled down. But if we go back up, this is a Bernoulli differential equation with a square over here. That means the quote-unquote n for the problem is 2. So that's why we substitute 1 minus 2, which ends up being y to the minus 1, which is the reciprocal y. Yep.
So the reason it's Bernoulli is because you have to use v equals y 1 minus n.
Yeah, I mean, the reason it's Bernoulli is it's that pattern. It's this pattern is called Bernoulli. If it's basically, it's almost if this was just, if we could just cover this up here, right? That would be just a plain old linear differential equation. So if it's just a linear differential equation with a y to the n stuck on there, that becomes a Bernoulli problem, which we can always solve by this clever substitution. Yep.
What if you weren't given the x is greater than 0? Because there was that ln that you used to absolute value.
Well, then we'd have to have a natural log of absolute value of x, but the absolute value of x would equal to minus x. So almost everywhere we've written, anytime we had a log, we had to have a log of minus x if we're working with x less than 0. Just that mostly. I try to avoid this because I don't think it's interesting. Yeah.
The example you did in class, you divided by, because you made y to the third, you divided by it first. So
yeah.
You do that for this one too?
You could do that for this one too, and that would make the calculation easier, I think.
Okay.
You know.
So it's like a solid round.
Yeah. These, you know, for context, I wrote these notes when I was working through the differential equations textbook when I first taught differential equations, like 2008 or whatever, no, 6, I guess. And so the first thing I did was just sit through the differential equations book and solve homework problems for 3 weeks. This is one of the ones I solved. So sometimes the way I've solved it is not like the most optimal way. Yet it's still like the mathematics is correct. It's just not as slick as what is in the notes I gave to you guys because, well, I wrote those this year. I like to think I've learned something, but yeah. That's really bright. Anyway. Okay, other questions? We have time for questions about the homework. If you got a particular question, I can try to field it. Yeah.
How do you like an initial condition, like like y, or like 1, 0? How do you do an initial condition?
How do we do an initial condition? Let's see here. I would say that is there a particular kind of problem you want to see the initial condition fit to, or just generic? So let's see here. How about this one? What am I? Example 4?
It was problem 49. It was dy over dx equals x cubed over y with an initial
y1 equals
X cubed over y? All right, so I'll make that an x to the 7th over y squared there. Okay, great. I changed your problem. So I would separate. I would integrate. And then you said you want solution through what?
It was y1 equals -2.
Y of 1 equals to -2. So what this means is when x is equal to 1, have y equals to -2, right? That's what that means. So we need to pick a constant to make it so. How do you do that? Yeah, we just plug this data into the general solution, see what happens, right? So I have 1/3 minus 2 to the 3rd power equals to 1/8 times 1 to the 8th power, which is easy enough to calculate, plus a constant. So apparently the constant we want is what? Minus 8/3 plus 1/8, excuse me, minus 1/8, right? Minus 1/8, which is like, oh, I don't know, minus 64 plus 3 over 24. And that should be minus 1/3. So we're both wrong. Let's see here, minus 67, so it's all good. Minus 67 over 24. 67, it feels prime-ish. Oh well, anyway, that's not really the issue. So anyway, solution, here you go. 1/3 y cubed equals to 1/8 x to the 8th minus 67 over 24, apparently. Now, did I say in that problem find the solution, or did I say find an explicit solution?
The explicit solution.
Oh, the explicit? Oh, how annoying. So, yeah, I'm just playing a dangerous game right here, because there's no guarantee when I just make up a problem like this that I can actually solve for y. I mean, probably. Can you solve for y? I think I can solve for y here. So for this problem, multiply by 3, I've got y cubed equals to 3/8 x to the 8th minus 67 over 8, right? Because 3 and the 8 and the 24 is 3 times 8. Okay, so and then y is what? Y is the cube root. Can you take the cube root of anything just willy-nilly? No concern. I mean, like, you can take the cube root of anything, right? And what I mean by that is there's no concern about domain, right? Square root, 4th root, these are problematic if you got a negative, but the cube root, the domain of the cube root is everything. You can take the cube root of a positive number, you can take the cube root of a negative number. Yeah. So that would be the explicit solution here. So that's a way you could do it. You could also do it the way I did it the other day, which was to like integrate the initial conditions into it as you're doing it. That's another way you could do it. But yeah.
Could you do another simple orthogonal trajectories?
Ah, yeah, let me show you one in the notes. Let's see here. Since I have this out here. So at the end of the thing I haven't covered yet, right, is the thing I haven't covered yet is the application sections at the end of the end of my first order article. Okay, so here's a couple of things we haven't actually. I don't think I've projected these yet. So example 6.7 is an example for you. So here I have. I want to find the orthogonal trajectories to dy dx equals to minus x over y. All right, so let me write the I'll write it over here as well, okay? So we have dy dx equals to, what is it? Minus x over y. That's given. If you want to find orthogonal trajectories to that differential equation, right, then what you do is you flip it and negative reciprocal of this, right? So minus 1 over minus x over y. But that's just equal to y over x, okay? So these will be the orthogonal trajectories of this one. So you take the differential equation you're given, and you negative reciprocate it, and then solve it. So this would be like, dy over y equals to dx over x. Integrate both sides. You get the log of the absolute value of x. Y equals to the log of the absolute value of x plus a constant. Exponentiate both sides. You get y is equal to plus or minus e to the c1 times x, which of course you could write as y equals mx. In other words, the orthogonal trajectory is here. Now you might wonder, like, where did this x squared, the dy dx equals minus x over y, I've solved elsewhere, and we learned that the solutions to that are circles, concentric about the origin. So here we found that circles have orthogonal trajectories, which are lines through the origin. Was a question? Yeah?
So all you do with that is you just take the opposite reciprocal of the equation and just solve like
Yep.
you would normally.
Yeah, yeah. Now, the one you have in the homework, I didn't give you a differential equation, right? I gave you a curve, and I said find orthogonal trajectories to that curve. How do you do that then? A little bit different, right? First, you have to figure out what is the given differential equation. So the next example is like that. See this one here? I say find the orthogonal trajectories to x squared minus y squared equals to 1. What is x squared minus, yeah, your question?
When you exponentiate it, wouldn't it be e plus or minus e to the c1 plus x?
I mean, you can,
Gotcha.
yeah. Okay, so this next example in the notes is one more like the one in your homework, all right? So this one here, see, I start with, let me blow this up a bit. So first of all, what is, question, what is x squared minus y squared equals to 1? Do you know what that is graphically? A hyperbola, right? This is a hyperbola, which I have pictured many of down here. So unfortunately, this picture is not just the hyperbola, right? It's lots and lots of hyperbolas, Let's see, that one, did that open horizontally or vertically? If we put x equals to 0, right? Is there any solution? You get minus y squared equal to 1. There's no solution, right? So the one that we're given in example 6.8, there's no place where the graph crosses x equals to 0, which is to say it's opening horizontally. So probably the one that we're given, the curve we're given, is probably this thing right here. Maybe here. So it's opening horizontally, and it's got vertices of plus or minus 1. All right. I sometimes call this thing the unit hyperbola. It's sort of analogous to the unit circle. Okay. Anyway, what's its differential equation? How do you find the differential equation of the curve? You implicitly differentiate it, right? So what I do is take this, right, and I take the derivative of it, which gives me 2x minus 2y dy dx, right? That's the differential equation, which takes the hyperbola as its solution. Once you find that, then you can find the orthogonal trajectory, because that gives me dy dx equals to x over y. So how do you find orthogonal trajectories? Well, you solve dy dx equals to minus y over x. And it turns out that when you solve that problem, you separate, you integrate, clean it up, solve for y, you get y equals k over x. Those are the reciprocal functions. So those guys are like these ones. You know, and down here, these would be like positive k's, would be these reciprocal graphs. Yeah, these positive k would give you reciprocal graphs like here. The negative k's would give you reciprocal graphs down here. Wherever those reciprocal graphs are cutting through the unit hyperbola, they're meeting it at a 90-degree angle. So don't get lost in the graphing. The procedure is actually very simple. Either you're given a differential equation, and you simply take the negative reciprocal of it and solve it. That's how you find the orthogonal trajectory. Or you have to create the differential equation from a given curve by implicit differentiation, then invert it and solve it to find the orthogonal trajectories. But that's it. Uh-huh.
So you use implicit differentiation to find the differential equation to solve.
Yep, that's right. Other questions? Yes, sir.
Do you want us to just like always replace plus or minus e to c with a different constant? Or
Depends on your purpose, but I usually just do to make it the solution like look neater. And sometimes I do it in order to bring that exceptional solution back into the fold, you know, that we lost with the separation of variables, like in that example I talked about at the start of all this. All right, shall I put this projector away? Okay. All right, so let's see here. Let me solve a couple of my applied problems in here. There's a preamble at the start of the application section about physics, which maybe I'll go through tomorrow. I don't think today is the right time for it. So I'll just try to work a couple isolated problems here in the time that remains, if I can. I guess we'll work here. So this is a relatively famous one. So example 6.3, you have suppose population P grows at rate directly proportional to the population. All right, let K be the proportionality constant. Find the population at time t in terms of the initial population. All right. So let's see if we can solve this problem. I think we can solve this one. So in words, what's going on here is you're being told that dp dt, right, which is the rate of change, that's the change in the population, right, dp dt. It's directly proportional with proportionality constant k to the population. So that's equal to k times p. That's the differential equation we're up against, right? Can we solve this? Yeah, separate, integrate, right? So we got dp over p. equals to k dt. Integrate both sides, yeah. Log of the absolute value of p equals to k times t plus, let's say, c1, which if I solve for p, I get, through the algebra we keep doing, p is equal to plus or minus e to the c1 times e to the kt, right? That same algebra we've gone through a couple times now. And what happens when you put time 0 into that? What do you get? Yeah, we get p sub 0 by definition on the left-hand side, right? Is plus or minus e to the c1, whatever that is, times e to the 0, which is what? Right, that's just 1, right? So that is plus or minus e to the c1, yeah? So my solution is just this. P of t is equal to p sub 0 times e to the kt. This is the very well-known formula for exponential growth, right? This well describes the growth of like bacteria in petri dishes and stuff like that, or isolated populations over sufficiently small time scales. But this always fails if you follow it for enough time, right? Every generation has some sort of doom and gloom population model that is going to always happen right around the bend, and it never comes to fruition for humans, at least. The things that actually change the trend of human population are those things that you can't predict. Like genuinely chaotic events, the plague, war, people giving up on having children, stuff like that. But anyway, so there's that. Now, the same mathematics describes radioactive decay, right? So like radioactive decay, if you talk about the number of particles present, you have dn dt is equal to minus kn. So here n is the number of radioactive particles. So you might be talking about, I don't know, the number of free neutrons, right? The free neutron has a half-life of about 11 minutes. So if you could somehow have a bucket of free neutrons, 100 of them, statistically speaking, after 11 minutes you got 50. The other 50 have decayed into a proton, an electron neutrino. That's a random, basically random event, but essentially it follows this mathematical law that the number that are decaying is proportional to the number that are present, according to some proportionality constant, right? And so in that case, usually you think about, I think of k being positive for the sake of our discussion. I put the minus in because radioactive decay, it's not growth, it's decay, right? But it's the same mathematics, right? Same series of steps will give you this solution, right? N of t is equal to n0 e to the minus kt. Here's a fun exercise, pre-calculus exercise. Can you rewrite that in terms of half-life? Like how long, I just told you for free neutrons, it takes 11 minutes for that. 11 minutes is the half-life, yeah?
You make your n of t equal half of your initial n.
Okay. So put n, so like n0 over 2 is equal to n0 e to the minus k. Let's say the half-life is, let's call it tau, for the sake of our algebra here, right? And that would give us tau equal to what? I guess we need to do some algebra, right? 1/2 e to the minus k tau, divide by the n naught, right? And so we got log of 1/2 equals to minus k tau. Apparently, tau is equal to minus the log of 1/2 over k, right? Which gives me that the half-life is actually equal to the log of 2 divided by k, right? Here's a bit more algebra for you. So this is our formula to start with, right? How would you rewrite that in terms of base, in terms of a 1/2 power expansion? Or let me rewrite this. Let me make it a little bit easier on us. N0 e to the kt. How would you write e to the kt as a power 2 expansion? What we're doing right now is not calculus. I'm just messing around. So, but I think this is algebra. It's good for you to see. We could take e to the kt and we can rewrite it as 2 to a power. How do we do that? How about this? 2 to the natural log of e to the kt. What happens then? My bad. That was supposed to be 2 to the what? If I'm going to do 2 to something and make it like legit, what do I have to do? My bad. 2 to the log 2, right? That's an identity. And how's that work out? See, that is equal to n0 2 to the kt times log 2 of what? Of e, right? What is log 2 of e? Do you guys know? That is the natural log of e divided by the natural log of 2 by the change of base formulas for logs. The natural log of e is 1, so this is really just 1 over log 2. Which means this is n sub 0 over 2 to the kt divided by log 2, which we could rewrite as n sub 0 times what? 1/2 to the what? What's kt over log 2? Well, k over log 2 over k was tau, right? So this is 1/2 to the minus t over tau. Or maybe not minus, but just t over tau. Yeah, t over tau, no minus. Which manifestly shows you when you put time tau in, what do you get? Half, right? See this? If I put t equal to tau, I get n0 over 2. What happens when I put t equal to 2 tau? n0 over 4, right? And so forth. And you keep having it and having it and having it. So there's something you should be aware of here in terms of the pre-calculus, which is that exponentials can be repackaged as either doubling formulas or halving formulas if you want. You just have to adjust the exponent appropriately with the pre-calculus. They're not separate problems. All right, let's get back to the calculus if you guys don't mind. Another problem, if you study a resistor and a capacitor and a current charging it, right? And then you charge up the capacitor and then you let it discharge. All right, if you sort through that, this is my example 6.4. What it brings you to, as you study the Kirchhoff's voltage laws and all that, and the definition of capacitance and so forth, you get to the following differential equation. Minus the resistance times the charge in the capacitor change rate rated dq dt is equal to q over c. All right, so if you're wondering like where that's coming from, it's just that the that's essentially saying that the voltage so this is the dq dt would be the current, right? You guys know that I times R is the voltage, right? So this is the voltage from current flowing. This is the voltage from the capacitor being charged, right? And they're equal but opposite because the sum of the voltages around the circuit has to be 0. Basically, the circuit we're talking about here is just this. It's kind of boring. you've charged up the capacitor, and then you take the charging, whatever's charging it out of the picture, and just put them together. This is what happens. This is your Kirchhoff voltage law. And the minus has to be there because the charge is flowing off the, that has to do with the fact that the charge is flowing off the capacitor, okay? So anyway, can you solve this differential equation? Well, yeah, we can, right? We do what? Here, by the way, the R and the C are constants here, resistance and capacitance. So separate, integrate. I mean, it's, it's kind of embarrassingly simple in terms of a differential equation. We have dq over q is minus R over C times dt. And if I remember right, we could just call that dt over tau, where tau is equal to C over R. Is that right? Negative C over R? There's a minus here. Is that right, though? I don't remember. I remember RC for the time constant. I wonder if my... See, this is why I need to teach physics 2 again. How did I get on RC? Oh, it's me. I made a stupid mistake. It's right on the board, right? Come on. Look at this, guys. Look at this. Come on. Look at this.
Yeah,
Really?
you're supposed to divide the R, right? Not
Yes.
the add thing.
Yes. If I could just do math, right? I mean, divide by R, right? Like you just... So, there we go. Is that better? But yes, the time constant is by definition RC. So that's a pretty standard notation here. Anyway, so if I integrate both sides now, I've got natural log the absolute value of q equals, minus t over tau plus a constant. And then that gives me q, and let me just get straight to the point. It gives you the initial charge times e to the minus t over tau, okay? And the significance of the number multiplying the exponential is it's the initial value again. Just it's the same mathematics we just gone through. So what happens, I mean, this is interesting. How long does it take for a capacitor to discharge? What's the graph of this look like, guys? The initial charge, let's say, is Q naught, yeah? And then it's got exponential decay, right? And so looks something like this, all right? So just some fun numerical facts for you. Here's about 1 time constant. Here's about 2 time constants. Here's about 3 time constants, 4, 5, roughly speaking. By the time you're to 5 time constants, you're something like 99% discharged, something like